Welcome back. It's Friday. I gotta sound excited because it goes on YouTube, and I've learned a thing or two about YouTube. I don't really have announcements today, but I'll just throw in a couple things. EMS, we have a pro seminar after this. Kathy Welch is speaking, so all of you are welcome, even if you're not in EMS, and even if you're not enrolled in the pro seminar. It's just supposed to be for all of us. And then afterwards, 3:30-ish, EMS social, right? At Unimpaired down the street here, right? Very good. So thank you to all of you who've organized and done all that. It's going to be fun. Hello, everybody online. Got a nice sized group online. Hope you can hear me. It looks like we have a question online before we get a chance. Would you like to go ahead, Jacinta?
Yeah, so I just wanted to clarify that I understood this fully with the distributions of the observed variable versus the latent variable for item response theory.
Yeah.
So the observed variable is the Bernoulli distribution,
Correct.
right?
Correct.
And then the distribution of the latent variable, that depends on the prior distribution and the distribution of the data, correct?
No, it's a definition. So we define the distribution of the latent variable as, in IRT's case, normal.
Oh, okay. Okay.
But, so yeah, this is about the formative assessment this week, the 4 questions. Factor analysis, the assumed distribution of the items is normal. The assumed distribution of the latent trait in factor analysis is normal. In IRT, the assumed distributions of the item is Bernoulli, or categorical of some sort. And the assumed distribution of the latent trait is normal. So those were the answers.
Okay.
I hope that helped a little bit.
Yes, it did. I got one of them. Yes, thank you. I understand.
Well, here's the thing. Just for trying, you got all of them. That's why we have those questions. So
okay,
thank you for asking. And this actually is going to be, we're going to keep underscoring this point as we go forward. What we call IRT and what we call CFA, or what other people call IRT or CFA, can be very broad and can be very difficult to understand where one stops and one starts. For instance, for IRT, actually for CFA, some people might say, well, I'm doing CFA with categorical items, which I would call IRT, but if they come from an item factor analysis world, that's what they're going to call it. So at some point, the labels don't do us any good, and we have to just understand the distributional assumptions that are being used. So that's sort of a different way of thinking than if you take a class and you learn Levon or you learn M+, and it's all those types of programs that will let you do different distributions. You'll have to call it something, but I just call it latent variable analysis or a measurement model itself. So losing the CFA and IRT as quick as I can. So, other clarifying questions before we begin? Yes?
What's the difference between burn-in period and tuning period or iteration?
So a burn-in period is technically the period from where you start a Markov chain until where it reaches somewhere near the center of its posterior. Each parameter reaches somewhere near the center of its posterior. Oftentimes, a tuning period is included as part of the burn-in itself. So we're going to, well, I'll just say it. I'm sorry, I'm getting ahead of myself a little bit. But for the Metropolis Hastings algorithm, this is a rejection sampling algorithm, one where we propose values from a distribution that we know that's easy to sample from, and then accept or reject them. The proposal distribution, to make it efficient, you sort of have to hone in on a standard deviation that's related to the posterior, that you have no idea of understanding until you start sampling. So what ends up happening is the first part of the burn-in gets broken into a series of what we call tuning regions of the chain, where we'll run the chain a very small amount of time, maybe 500 iterations, take a look at the posterior standard deviations, adjust the standard deviation of our proposal distribution, and repeat that process. So it's like tuning is often part of the burn-in, because the whole time we're tuning, the whole time the chain is moving towards convergence. But in those segments of tuning, we might change certain features of the algorithm as we go forward. Once we're done with tuning, there still may be a period of burn-in that we discard, but that we're no longer changing the specifics of the algorithm. There's a lot to that. It's hard to really tell you without having it in front of us. So if you want to ask that again when we get to the algorithm, I'd be happy to talk more. Okay? Other questions? All right, so I'm going to start off where we thought about steps in a MCMC analysis here. And I've turned off the multiplex. So those of you in class, I didn't even know this could happen. And thanks to Shihong for mentioning that. Anyway, remember the steps in an MC analysis. We've got to specify our model. Part of the model is the set of parameters that we're including in it. And then for every one of those parameters, we have to specify a prior distribution. Got to build the model syntax. I mean, that is not trivial. I've spent literally all morning building syntax for a different model than I'm using JAGs for. It's taken an excessively long amount of time, but I needed to do that. We start running our Markov chains. Once we're done, we check to see that the chains have converged. If they have not converged, we go back, try again, either run it longer, change the burn-in, change some of our model priors. Once they're converged, then we interpret and report results. Pretty straightforward, huh? Not really, but well, this was the model that we're going to play with today, the empty model. Next week, class will be a Lisa-style example, like a handout, she calls them. It'll be our markdown. So instead of some slides, it'll just be all document format, and we'll walk through the analysis of all the data going from start to finish. That's the plan, at least. So the model has two parameters. We have beta 0, and we have sigma squared error. Not only that, the variable, there's one variable, it's just weight, the weight of a person in pounds. So we talked about Stan. Stan's a really interesting program because it will compile your syntax. It'll take the syntax of Stan, translate it to C++, which is a compiled language, compile that syntax, and produce an executable program that only runs your analysis in your model. So it cuts out a lot of overhead that shows up. There are several algorithms out there that do real general likelihood-based estimation. One of the first I was familiar with is something called proc-NL mixed in SAS. You may have heard of that before. There are other ones out there as well. They just run very slowly because there's a bunch of overhead involved to try to figure out which distribution, how things work. So Stan tries to cut out over that overhead and create something that's much more efficient just for your code. Let's see here. So Stan is nice because if you're in RStudio and you want to create a Stan code, you can go under this new file menu and where'd it go? Right here is the Stan file option. So you can pick a Stan file in RStudio and hey, lo and behold, out it comes. The other nice thing about this, the thing that's really helpful, particularly when you're learning Stan, is that if you type something incorrect, of course it's not going to do it for me now. Let's see if that does it. Probably not. It has, here, let's try this. Yeah, there it is. It tells you where your error is. Like I took off a semicolon at the end. So parser expected semicolon. So you put that back, save it, fix it. Oh, wait, there's an error, parser expected. So that basically it's allowing you, the nice thing about integrating Stan code with RStudio is that it gives you, RStudio has a set of debugging tools or a set of syntax highlighting tools that will tell you where your Stan code isn't coded the way it expects it to be. This is tremendously helpful. if you compare it to JAGs, for instance, JAGs, I literally got to like 90 decibels yesterday because of JAGs, right? That's how like my watch was like, it's loud. Yeah, that's me. Right? And so JAGs is, you write syntax in R, you pass it to JAGs. JAGs comes back with an error that says something like, invalid parent for child blah, blah, blah. What the hell does that mean, right? Stan is much more efficient. Stan is much more friendly when it comes to that. So I'm really actually quite impressed with the way they've come a long way with Stan. It never used to be like this when I started using it, but now it's become quite useful. So Stan files themselves are text files. So they're just plain text. And if you look at our code that's online, you'll see there's a model00.stan file in the folder. It's just plain text, just like the R syntax file is plain text as well. And remember, Stan itself is a program that stands alone from R in RStudio, although I use RStudio to interface with it. But in theory, you don't even have to use any of the R stuff at all. You could create your own plain text file for Stan and then submit it to the executable that Stan creates on your own, although it takes a little bit more work. So, how are we doing so far? How many of you used Stan before? One person, two people, three? Maybe three. So is this new to you, most of you? Excellent. Okay, that's what I'm hoping. And I'll look online, but that works too. All right. Back to the pres. So RStudio creates one of those files, does syntax highlighting, very useful. You can also build Stan syntax within R itself. So when you get really proficient at Stan, you can create Stan syntax like you see here, this Stan model file. By the way, I'm in the R file that shows up in our directory. So rather than having to sift through what chunk of code I'm in my markdown file, I'm just in the R. I put all that into just a linear R file so you can see how it works. So this same Stan code right here can be thought of as a character vector. So Stan model is just a character, and if you really want to see it, output it with the cat command and it looks like Stan code. There's no difference to Stan about how you create your code. Once you're really proficient at Stan, I think using it in line in R is helpful because it keeps you from having to have one file per analysis, which is a problem. But to begin with, I highly encourage you to write your Stan code as a standalone file in a directory. How are we doing? I'm going to get to the sections of this. It's coming. Just sort of big picture first, and then I'll hone in. Questions? Gotcha. All right, so let's talk about the syntax a bit, shall we? So this is the syntax for the model we're going to run. The model with those two parameters, beta 0 and sigma. Notable about Stan, every line of syntax where you just say something or do something ends with a semicolon. So it's very much like SAS. What is the acronym that people joke about with SAS, searching for a semicolon? SAS, something like that? Anyway, the nice thing about SAS is, or Stan is that, again, if you're using RStudio to develop Stan code, it'll tell you if you miss something like that, so that's nice. The other part of Stan code, these double slashes indicates a comment. That double slash is a feature of C++ language. That's how you comment code in C++. So far, so good? So down here, these are comments, and again, RStudio is nice because it'll take those comments and make them green for you or change the color of them so you know that they're a comment. Very helpful. Okay, so Stan has a series of blocks of its syntax that Stan expects to have when it runs. Those of you who run M+, this is very similar. M+ has a data section, a model section, and so forth. Stan, very similar. 3 blocks for us to get running. There are actually quite a few other blocks that are involved, and throughout class, we'll be adding blocks to this. Some blocks create brand new parameters themselves out of model parameters. We're going to see that next week in the linear models example because I have an interaction in there. We might want to do simple slopes so we can actually get a simple slope posterior distribution even though it's not part of the model directly. Other blocks will do things like posterior predictive model checks, which is the way we look at Bayesian model fit. So that'll come as we go later on. But the three that we have here, data, this is what Stan expects you to send into it to run. We have parameters, which is what Stan thinks you will run a model out of. And we have the model itself, which is where you define the prior distributions and the model data likelihood. Now, the model itself will typically depend on parameters. So if you name a parameter in the model that doesn't show up in the parameters block, it's going to yell at you. Politely, but still. Not as loud as I yell at Jax.
I'm assuming order matters for the blocks, or no?
Not that I'm aware of, but I'm not sure. Try it out and let me know. The other part of this is, so many of you have had my spouse's homework system where you can get your own data set, do your own analyses and results. That isn't going to fly for us in this class with Stan, because it turns out with the random sampling that we're doing, the order in which you put your model code determines sort of the order in which parameter values get randomly assigned. So that means I can have the same model as you, and I might switch a line of code and therefore change the sequence of random numbers that are drawn for each of our computers to have it work. So,
But even if we had the exact same code, if it's random, wouldn't it also differ?
potentially, we can save a random number seed, which will be a starting point. However,
I know all about Minecraft seeds.
oh, there you have it. That's exactly right. However, if your computer architecture differs from mine, it may be different. And if your operating system is different than mine, it may be different. So that's part of the problem with this. In the Stan user's manual, there's a whole section on reproducibility. It basically says, yeah, on the same machine with the same number seed, the same code will give the same results. You change the machine, you change the number seed, you'll get different results. Now, not always with the machine, but it can happen depending on the architecture, what type of chip you're running. So, and what type of operating system as well. Yeah.
More like real life question.
Yeah.
Do you normally specify a random number seed
Yes.
to be able to replicate?
Yes, I do. It's good practice to get into, although I don't know if it's actually in my code here. I hope it is. I think it is. Pretty much everything we're going to do in this class is going to involve random numbers. And so I can give a little bit more detail on that in a later lecture, but the idea of the random number seed is if you have the seed value that starts the number sequence, that on your machine it should be the same. Other questions? Okay, so let's talk about the data step and the parameter step. This is a difference between Stan and R, or Stan and Stata, or Stan and SPSS. Wait, I don't know SPSS. Whatever you use for your stat package. Stan functions like a compiled language, meaning when you declare a variable, like either the data coming in or the parameter itself, you have to tell it the type of data it expects. And the type of data means the type of data as the numeric object that's in the computer itself. So in the data section, you'll see here I have int, and then an option. Whoa, that's not cool. Lower equals 0, meaning the lower bound of that integer, and then a value n. So what Stan expects here is that n will be an integer value, an integer type variable. Integer variables are a very, very specific class of number that gets saved a certain way on your system. The vector below this, vector ny, this is saying I have y, it's going to be a vector or an array of n, capital N numbers, right? So let's imagine I have 30 observations. n would be 30. We then use n in the next line, and we say we have 30 weights. That's what it says. We're inputting 30 weights. When you use the word vector, Stan assumes you're looking at a floating point number. So the difference between integer valued numbers and floating valued numbers in a computer is that integers are the discrete integers that we count with. They can be negative as well too, they're signed. Floating point numbers are decimal numbers. Okay? Thankfully we don't have to specify how many bits of precision a floating point number is, because in C and C++, Fortran, you may have to say a real that's real 8 versus real 4, 16, 32, or 64-bit precision. We don't have to do that. It goes with the max precision of the machine. I think it's all 64 these days anyway. Finally, the vector itself is full of if you only have one value of it, you don't need to put the word vector there. You just define the parameter as real. That real says it's a floating point. So beta 0 can take any number that's on the real number line, from negative infinity to positive infinity, including decimal fraction values. Whereas this n thing right here, if you give it 1.5, it's going to throw back an error saying, nope, that's not an integer. I need integer value data to come in. So that's one of the big differences between, if you have not used a compiled language, again, C, C++, Fortran, where you have to define everything and their type of data, this will be a little bit of a difference, but once you get used to it, it's not that bad for what we do. Okay, any questions? Yes.
In line 12 and 13, we can see that we are using the normal for beta and uniform for sigma, but in the squares, that's 0 and 1,000, and then 0 and 100,000. What's the meaning of those?
I'll get to that in just a moment. But, I'm going to stay on these first two blocks right here for just another slide. There's one more other thing I need to say, it looks like.
So,
Yes.
it's vector again.
Vector
Yeah.
is an array of floating point numbers.
Okay.
So when you, let me, again, getting a little bit ahead of myself, but if you look in R, our data itself, this diet data, even though the weights are all integer valued, we're going to call them floating point. And so we're submitting this long row of data right here. That is a vector. That's an array itself. So the array, a vector or an array has a length to it. And this has 30 is its length. So we have to
It's not the full matrix.
It's not the full matrix though. We could input the whole matrix and just pick a column of it to do our analysis on, but we're going to just stick with something that's understandable. The other thing about Stan code, I should say, is that there are probably, for every analysis, there's probably 30 ways of doing it slightly different. Some are more efficient than others, but the first rule, at least in this class, of getting things to work is getting things to work. I don't care how efficient they work. Make it accurate, make it slow, we'll make it work after that, right?
What if you have a missing value? Would you take the expected, the expected array length, or would you already just feeding your data as cleaned?
There's a couple ways of handling missing values. Stan is different than JAGS in this regard. So if you hear JAGS, you just submit data to JAGS, missing or not, and it's fine with it. Stan will not model directly the missing data unless you tell it to. So typically what I've done is submit the whole array, but also then submit a little indicator array that says whether or not a value is missing or not. And then I make a code switch to say, if it's missing, skip it. If it's not missing, do something to it.
So location doesn't matter in the missing value, it's just that there is some length of missing value.
That's right. That's right. Yeah. Good question. And once again, when you put an array into Stan, it expects you to tell you how long it is. So you have to know that going into it. So you need to tell it the dimensions of the array. There's another type of data that we'll use pretty quickly is matrix, which is a series of vectors. And it will have 2 dimensions to it. Again, you'll have to name both of those. Finally, you see here under real beta 0, I don't have any modifier to it. I don't have anything in little, what are those, brackets? Those aren't brackets. Within the little carrots, thank you. That means Stan is going to start beta 0 anywhere on the real number line. But for sigma, that's a standard deviation. And we need the standard deviation to be bigger than 0. So we put lower equals 0 though. Now technically it can take a value of 0. The likelihood of it being exactly 0 is 0. So it'll be a floating point number that'll be on the positive side when it starts. Yeah.
Do you have to specify these? Because,
Not always.
okay.
Not always. If you have parameters that can only be in a certain range, yes.
I guess it's more my question than for the data of like, what's the benefit of specifying bounds there? When it's just like, I know it's an integer.
Yeah.
Let it go in, integers will go in.
It's overly redundant, and it helps protect your code. Like if you have a bug somewhere in your code, it'll throw an error if it doesn't fit with the expectation.
Okay.
So it's a sort of a way of putting some constraints on to limit where errors can happen.
Checks,
Yeah,
yeah.
but I think quickly you find out that anything you import into Stan, you'll probably have a good sense of what that is. That actually speaks to one of the problems with it, and that's why it sort of allows this in the beginning, which is we have our data in R as an R object, but we need to get it into Stan as a Stan object. And so there's multiple places where that can cause problems. And when something doesn't run, it's hard to pin down where it is, and I think this is where Stan's way of saying this will remove a few of the other options of where that error might be. Okay. Technically speaking, this whole process where you define a variable's type is called type declaration. I've heard that before in a computer science class. There's jokes. When I used to do Facebook, me and my Facebook psychometrician friends would make a joke. One of my colleagues put up there. In Fortran, you can turn that. You have to turn it on explicitly. It's called explicit none. And he's like, "Yeah, explicit none. Those are for cowards." And that resonated really well back like circa 2011. So that was really funny. But now I don't do anything with Facebook. And I don't really make jokes. I just go to sleep every night, wake up in the morning, and be glad for that. Sorry.
I know you just explained this to Cass, but
No problem.
I don't think so we set the length, right?
Yep.
What happens when you have missing data? Does it basically just like,
No, the missing data occupies space in the vector.
okay, got it.
It's
Cool.
still
Thank you.
there. It just has a code to it that's not. It allows a missing character in there, but it doesn't know what to do with it when it gets to the model.
Got it, thank you.
You're welcome. Other questions? Anybody else? Okay. So we again have lower 0 for sigma. If you are interested in lots of the data types that are out there, you can go to the Stan reference manual. I put a link at the bottom of the page, but it'll tell you all the different types that are out there. I would tell you to bookmark that for this class because you'll spend a long time in the reference menu trying to figure out which places go where, and I believe I try to put a link for that. There it is. Stan documentation is on this class right here. There's a user's guide that sort of tells you how to run certain models. The language reference, which tells you what needs to be in the code. The functions reference, which tells you the types of things you can do with other parts of the code itself. And then this CMD Stan, which is the thing we're trying to use to move data to and from Stan itself. So as you can see, there's a lot to this. So that's why I'm trying to go a little bit slow at the beginning. Let's talk about that data step. Vladimir, your question. In the model section, you define the distribution needed for the models and the priors, right? So remember, part of the CMC analysis, what are the parameters? What's the model for your analysis? And what are the prior distributions? Here, we had two parameters, beta 0 and sigma. And I'm going to start by looking at the data itself, the data step. The model for the observed data, we decided was y is normally distributed. The mean of y is beta 0. and the standard deviation for y is sigma. Now look, that's a standard deviation. I had to figure that out by going into the stand manual as to what it's expecting in the second argument to the function normal. But basically there's this normal function right here. It needs a mean, it needs a standard deviation. But you'll note that the things that comprise either side of the comma in this function called the normal function are parameters. So what it's doing is saying, you've got model parameters, we're going to put them into the model itself and make it run based on that. So again, the two components of that, mean and standard deviation. If you go to the function reference and go to continuous distributions, this is where you'll find it, under normal distribution, you'll see the statement itself, and this is how you can tell what goes where. Mu for the mean, sigma for the standard deviation, and you'll see sigma and mu, although they didn't use the characters down here, but those are the names of those variables above. Questions on that so far? Okay. Furthermore, we then define the prior distributions for our parameters. So for instance, beta 0 is a prior for beta 0. Now I haven't talked about what makes a good sense for what the prior is. That's coming in our next handout. So for now, we're just going to assume, with lack of any evidence whatsoever, that we're going to put a prior on beta 0 that is what we call highly uninformative. So we're saying the mean of the distribution of beta 0 should be somewhere around 0. And the standard deviation of that distribution should be somewhere around 1,000. So if you can think about what that tells you about our belief about beta 0. Yes, the mean's at 0, but if you think of a normal distribution, plus or minus 3 standard deviations is about 99% of the probability mass. So that means we think beta 0 is somewhere between, most likely, negative 3,000 and positive 3,000. Is that a good idea? I don't know. We'll talk more about how we pick that pretty soon. I will tell you, if you look at if you know a little bit about the model, here's our weight vector. Beta 0 will be the mean of the weights. The mean of the weights certainly is within that range. Now, if this weight vector was weights of aircraft, right? And these were not 3-digit numbers, but 6-digit numbers, that prior would not work very well because the mean, it's saying the mean is somewhere between negative 3,000 and positive 3,000. But if the mean is 300,000, that's going to be off.
Yeah. And posterior, the next step of that will refine this wide range into why it fits with the data.
We'll talk more about that. Choice of prior for linear models is somewhat difficult. For latent variable models, it's actually a little bit easier. But the reason why the choice of prior for linear models is difficult is because of the scale of the variables themselves. Right? Each of our parameters are going to have something to do with the scale of either the outcome, the predicted value, or a ratio of units of the predicted value per unit of a predictor, right? The slope. So when we put in our predictors here, our x's have units and our y's have units. And the betas are on the scale of those. So it's difficult to tell what they're going to be ahead of time, but we'll talk about that when we get to the big example. For right now, I'm just going to wave my hands. Again, I ask you to do magic a lot. The magic is trying to give you the big impression first, and then we'll go into the details once we get the big impression. Okay. Did I see a question?
Well, I don't know if this is a detailed question or not. Anyway.
I'll try.
Connecting it back to like the intro phase lecture.
Right.
We were talking about like informative and uninformative.
That's
progress.
right.
That's where that concept shows up is here.
That's exactly right. All right. And what informative versus uninformative happens to choose is how much probability mass is concentrated around a small area. When you look at our vector of weights, the mean is somewhere, okay, we ran a linear model. I think the mean was like 171, right? So for us, mean is 171. Our beta distribution, our prior for it saying the mean is 0, which is not close to that, but the difference between 0 and 171 in the likelihood when the standard deviation is 3,000 isn't very much. So you have to look at the shape of the prior and think about how high the peak of it is to really get a sense for how informative it is. But we're not, we'll get to that more next week. I want to give you enough detail to keep you going.
I'm
But,
okay.
this is the problem. Like last time I taught this, I went from like the fine grain and I lost the big picture. And this time I'm trying for the big picture and I'm losing the fine grain, but we're going to fill in the fine grain as we go forward. So I apologize if I didn't tell you that motivation before. Yes?
In the case of beta sub 0, if we're using a normal prior, so we're assuming that we could have negative values, for example?
Yes.
But in the case of uniform, can we have negative values for sigma?
You cannot.
So that's not skewed.
It is skewed, yes. So sigma is interesting because sigma itself is a variance. So we can't have a negative variance in our analysis. A negative variance will, well, actually a negative variance will make this value right here negative, which makes a likelihood negative, which wouldn't work out. Like there's a problem with that from a conceptual point of whether a probability mass should be there. And so we technically can't allow sigma to go negative. So we have to find a prior that fits its range, that starts at 0 and goes up to positive infinity.
Okay.
Turns out finding a prior for variances, there have been a lot of words typed about this, a lot of ink printed on this subject. And I'm going to go with the bold claim that I'm agnostic, and that if you pick a prior one way, someone's going to turn around and tell you that that's not the prior they would pick. Of course it's not the prior they would pick. So I put uniform here because this is the quintessential definition of an uninformative prior. A uniform distribution has an equal probability or equal likelihood for all the values in the range that you give it. So here we're telling it, I don't know, that the standard deviation should be somewhere between 0 and 100,000. Now, if the standard deviation is more than 100,000, we have a big problem because the uniform won't go that far. So that is our prior for sigma. Did that answer your question? Other questions on that? So here's the big irony to all of this. If you notice the stand code that I created when I went down and I asked it to give me a stand file, they don't actually put the prior distributions in the model. So by default, if you don't specify a prior, what stand does is gives you what it calls an improper prior, although I don't necessarily think it's improper when you think of the computing language. Prior itself, it gives, is like a uniform prior around the space or the range of the variable itself. So here, because it said sigma is equal to 0, or is lower bound of 0, its prior it's assigning for sigma is a uniform distribution across all positive values. And mu, because it doesn't have a bound, is a uniform distribution across all values, all floating point numbers themselves. They call this improper. It's only improper if you don't think how the computer works. An improper prior, by the way, is a prior that doesn't have the right type of distribution. The distribution itself doesn't have it's not a proper, what is a proper distribution? We need a distribution to follow the range of the parameter, and we need it to integrate or sum to 1 to give us a probability region. What it's doing here by basically multiplying the likelihood by a value of 1 is saying that the integral of that is not equal to 1, but it's proportional to what it should be. It's still uniform, though. So that's a little too much information right now. Yeah.
So uniform distribution for sigma means like each single value have the same
Prior likelihood. So it's saying we don't have any belief that any one value of sigma it has a higher likelihood than any other from a prior belief sense.
Yeah.
So it puts the same weight on each possible value that goes between 0 and 100,000.
And back to the linear model, is
Yes.
this like contradiction with the assumptions of the linear regression that it is normally distributed of residuals or the error variance?
Well, So remember, in linear regression, sigma is the parameter that goes with the residual, not the residual itself. Right? And so what the regression says is that y follows a conditional normal distribution. Now, for us, the conditional part would be what we put in the mean, but because this is an empty model, it's actually unconditional. We would put in the next week when we get into the example, we'll see predictors in the mean spot, right? That's its conditional mean. So because of that, that error term is not actually sampled. But when we look at the distribution assumption, when we go back to the modeled equation and we say what's the distribution of y, and we look at the constants and the variables, and we say it's normal, that's where sigma comes from. So because of that, this fits precisely with what the assumptions of the model are.
Yeah.
Because we assume normal error, y gets the assumption of being normal. That's where that comes from. So here's the other fun thing. If you don't like any of the distributions you find in STAN, you can create your own distributions for the prior. You may ask why you want to do that. There'll be plenty of reasons that you encounter in your life as you go forward. I can't anticipate all of them now, but we'll get there. One of them, well, you want to hear one? Okay, in a factor analysis, a confirmatory factor analysis, which I know some of you are taking that class right now, you have to decide which items map on to which factors. Well, that can be hard and people don't like that. But an exploratory Bayesian version of that would be to try to say each item may have a probability of having a loading of equal to 0, and then some other continuous probability where it's not equal to 0. It's sort of a mixture model prior itself, where sometimes it takes the value of 0, sometimes it doesn't, to try to give it the chance to move off to 0 in some of those cases. That'd be one example. There are other examples as well. But generally, those additional distributions for priors involve some type of mixture of continuous and discrete distribution. At least that's the places I've seen it. But it really takes a very specific reason for doing that. How we doing? Okay, so we have our syntax. Hooray! I'm going to go back to my R code now. The big thing about this is now we need to tell Stan, take this syntax file and turn it into an executable program. Now, do you want a quick definition of executable program? R is an executable program. If you're using Windows, any program with an extension .exe, which means when you go to run it, it starts to use processing. It's made of compiled code, right? There's something called a compiler that translates C++ code into something that runs on your machine, right? It's like if you're using an iPad, it's the app itself. That's the executable, right? So what Stan is doing is building a standalone program for your analysis, just specifically to your analysis. So we actually have to tell it to compile that program. And that's where the CMD Stan R stuff works best. So up here, let me get there. When you have a file somewhere and you've loaded the CMD Stan R library, you can tell, actually, let me just delete this real quick. Oh, that's not what I want to delete, pardon me. If I don't do that, it won't compile. You tell it Stan model, and you tell it the file. It then begins compiling the program. If you have an error in your Stan syntax, this is where you'll find it. It says compiling Stan program. And then you'll see in my folder, there's this file that doesn't end in any extension named model00. That's the actual executable itself. That's what runs it. And here's the thing. If you are using Stan in some type of file-saving folder, OneDrive, Dropbox, Box, anything like that, where you have like a work computer and a home computer, where you have different machines. Heck, I've got one in the basement, one upstairs. If you compile it on one machine and go try to run it on a different one, it's not going to like it, usually. Right? That's not entirely true. If your architecture is all the same, it should run. Mine, I have an x86 version of a Mac at home, and I have an ARM version of a Mac, and they don't work the same, right? So what does that mean? You may get an error in this line. If you get an error in that line, look to see if you have that executable in your directory, delete it, and recompile. What Stan is doing while it's compiling is it's first checking to see if an executable exists in your folder. If it does exist, like I just created it, if I run this again, you'll see model executable is up to date. It checks to see if it's the same executable from the same C++ file that would render it. So it takes a while to compile things. It takes a few seconds. And the more complicated the model, the longer it takes to do the compilation. So it skips that step if it's not needed. But if I go and I change something, for instance, let's just make that a comment. Then when I go and rerun this line, you'll see it will recompile the program itself. So every time you change your Stan input file, Stan will have to recompile it to change it to make it work. This is an important step because when we get down to running our analysis in Stan, running the analysis itself will need that executable. And if it's not up to date, you're running an old model. So you got to make sure you always compile and then run. Okay? Every time I say okay, I feel like, ever watched that show Beavis and Butthead? It's back, by the way. I'm from the 90s. And that show is, and they make fun. It's totally for like my age demographic. It's just built for me. But there's a character on there I sound like, Mr. Van Driesen, when I'm like, okay. Like it just comes out. So, wait, yes. So, you built your file. You can find out its location. That's where it put it. You could also, if you had put your R file, if you put your syntax into R as an R object, you can also use the Stan file option, but now you wrap that name of the object. Remember, an R object is just this character string in R. You put it to write Stan file, put it through that function. It will take that character string, write it to the disk for you, find it, and then compile it for you. But if I do it that way, the location of it is very different. You see, that's the location in my disk where it put the Stan executable. Stan executable is when you do it from a write from file and don't tell it the full path. We'll just use a weird default path to it as well. So, kind of weird. Very different way of thinking about data, right? Questions? Let's see. Back over here. All right. So this is a little bit different than if you used rstan. rstan itself, some of you have had some real hard times getting cmd stan r to install, whereas rstan did install. If you did use rstan, then the compilation of the model and the running of the analysis is built into one function. So you don't do it separate. So that's a big difference. We'll get to that when I cover the rstan part down in just a little bit. Okay, so we compiled our Stan code. Sorry, we wrote our Stan code. We then submitted it to the compiler. It compiled our Stan code. And then finally, once we've built our, by the way, speaking of compiler, those of you on Windows machines, did you have to install RTools to get Stan to be installed? That's RTools includes the compiler that takes the C++ and translates it into an executable for you. So that's why you had to use that as an additional feature. Anyway, the thing we have to work on next, just went back, is putting our data, getting our data ready to put into Stan. Now you remember, in our Stan syntax, I told Stan to expect two pieces of data, two pieces of information. One is a single number that talks about the sample size, n, and one is a vector, or an array of numbers, that's equal to n, the length is equal to n, that's floating point. In R, we then create data using a list itself. Are you familiar with R list objects? Lists in R are ragged arrays. They're sort of arrays of objects. So what's an array? It's a box, a container that you can access what's in it either using a number or a name. Right? So here, stand data, if I type names, it will tell you there are two parts. There's an N and there's a Y. So if I type stand data and I use a $ in R, N will be 30 and Y will be a vector. So what CMD stand R wants you to do is to take every name of the variable that you find, every name of the data that you've specified in your data step, and name it that as part of the list of data that goes into stand. Right? So here, stand data has all of the things that you told stand to expect in terms of data coming in. If you don't have something in there, stand will not like it. Stand will tell you, hey, you don't have N. What's your problem? You told me there'd be N here, or something like that. Right? Any questions about that? Hey, Nathan, I just noticed you had a question. Do you still want to ask that?
No, I think you got the uniform.
Cool.
Prior was what I was asking about,
Okay.
I think.
Awesome. Sorry about that. I didn't see it. But if in the future, if any of you online put something in chat and I don't see it, please just unmute yourself and let me know, okay? Thank you. Okay, so we have our data. We will use this list, an R list of data. So every time we have something else we need to add to stand, in terms of data coming in, like next week we're going to have predictors. Well, guess what? Predictors are going to be in their own matrix. We're going to tell Stan in the data section, expect a matrix of predictors coming in. And then in our R code, we will have to add that matrix of predictors to our data list. Okay? Okay. If ever you're confused about whether your thing in R is a list or not, use the class function. That class function should say list. But if you define it as a list using this list function, the output will be a list, unless there's an error. Okay. Questions? All right. So now comes the fun part. Believe it or not, all of that it took before we could run the Markov chain. But now we have the stand data, we have the compiled executable, we have the stand syntax, all that stuff has been done. We can tell it, hey, we would like you to go and run a Markov chain. So the file that you created up here, the object nar, this model 00 from file that I'm calling it, is our stand object that will be the executable. In fact, if I type class for this, you're going to see something interesting. It's class CMD stand model, which is a CMD stand is the library we're using. It's also something called an R6 object. If you're not familiar with R6 objects, first of all, they're amazing. They're awesome. If you really want to know why, ask me. I'll spare you the details. Actually, I'll just say it. Forget it. In R, when you pass data to a function, when you say, I'm going to go send data over into stan or something like that, it has to copy all that data on the machine and make another copy of it to have the function do its work. Right? It's called passing by value. Right? An R6 object stops that from happening, meaning when you go and tell it, I want to sample things or I want to send data to it, it just passes by reference. It finds the location on the machine that's storing the digits that it needs to create your data and passes those locations rather than making another copy. Why that's important is copying data, even internally, takes time. And Markov chains are very large objects. So the more that we have to copy things, the more we have to take more time from the analysis itself. It's an efficiency thing. But R6 objects work a little bit differently. And this is where you might pull your hair out a little bit because it's R. The R6 object, you'll note, you may have seen it right here. Normally in R, like my stand data, $y, it just tells me the data. Turns out you can embed functions after a $sign in an R6 object. So when I wanted to figure out where the exe file was, I didn't pass this to exe file as a function. I did $sign function label. It's a little bit weirder than normal. For us, what's that mean? It means when we create our compiled stand object, in R, it has the function we need to do the sampling. So we just put a $sign in sample at the end of that object. And that becomes the function that does the sampling. So here we tell it our data. I gave it the best random number seed, number 1. Ooh. That seems to be always my number seed these days. Sometimes I put the date. Anyway. Number of chains, I'm going to do 4 chains that are run in parallel with the warm-up iterations of 1,000, which warm-up is Stan's language for burn-in, and sampling iterations of 10,000 also. So those are the options I'm submitting to sample. Now it turns out you can still see all of the options if you go into the parentheses and press tab. You will see all the different options that you can send it. But it's just a little different than calling the function itself in R. The object has the function embedded in it as the R6 object. R6 objects are a little bit more object-oriented also. They're mutable. You can define other objects that inherit some of the properties from the objects themselves. So if you're into coding, R6 objects are much more familiar to object-oriented coding than the rest. Okay, so in CMD stand R, use a sample, makes that work. Let's run this. We just run this code. What you'll end up seeing is that did not take long at all. So underneath the scenes, what's happening is the CMD stand R takes the data, outputs it, and passes it to the compiled object that it made for you, that your very model-specific executable, and then runs the chains as it's told you told it you wanted it to do. And it spits out the progress. Chain 1, 2, 3, and 4 here, although these do not look to be in parallel. Wait, there we go. Got a little mix of 3 and 4 here. Maybe not. Anyway. So it tries to run these separately in separate processes on your machine. They all ran, everything finished, which is great. If you're not using CMD stand R, if you're using RStan, I'm just going to show that to you real quick. To make it go run in parallel. So first of all, what is parallel processing versus serial? In parallel processing, so your machine, each of your computers, its microchip has a series of cores in it. A core is a part of the computer that does the processing of a bunch of instructions in serial. But the cores can run independently of each other. So we take advantage of that with a Markov chain analysis because we take a computer, mine has quite a few cores, it says, okay, I'm going to run 4 chains. I'm going to take 1 core per chain and run them at the same time. So instead of, if you did not specify it to run it parallel, you'd have to run those chains back to back. So it would actually be a little under 4 times as long. It's a little bit of overhead the computer does that takes time to parallelize. The same thing works here. The parallel package, my computer has 10 cores on it. I'm only going to use 4. And so in R, the process of the parallel package running in R, you see, when it starts to run, you start to see this starting worker right here. That basically says it created this little miniature cluster of computers that are using 4 separate processes. PID is a process ID, and it distributes each of these analyses to each of these cores in your architecture. But there you went. It's done. One other thing I will note, in the RStan, I think one of you had a question last week, how will you know how long it takes Here's the warning. It says 1,000 transitions using 10 leapfrog steps per transition would take 0.05 seconds, right? The more complicated the model it takes, that might say 15 seconds. I mean, it take 20 seconds. So it'll say, basically, it's giving you a hint as to how long it thinks it's going to take to do a lot of what it's doing. Okay, how we doing?
Given the notion of cores and everything, is there anything that you found kind of overloads the computer if you're running analysis like this and working on other things? Like, is there anything that breaks this?
Good question. If you max out your cores on anything, you're going to slow everything else down on your computer. I don't remember the order in which it prioritizes processes, but pretty sure if RStudio is your window that's open and you tell it to use all the cores, everything else going on in the background, including necessary computing tasks, will start to grind to a halt. So you want to try to make sure that you have the number of cores less than the total number of cores on your machine. So a lot of times, what you'll see people do is detect cores minus 1. So basically, detect cores tells you there are 10 cores up here, but you only want to use 9 of them at most. And for our purposes, it'll only use 4. But that's a really good question. Yeah, you can quickly make your computer stop in its tracks. In the early days of multi-threaded programming, which is what it takes to do this multi-core stuff, the compiled languages had really weird add-ins that sort of did this. And I can tell you the number of times I literally had to stop everything I was doing in coding and restart the entire system because I crashed it or overheated it or something like that. So, all right. Other questions? All right, all that just to run a single analysis. I'm selling you on Bayes, aren't I? But the reason why people love Bayes so much is because if you endure all of that, you just really love your numbers more. It just shows you how much love you have for your numbers, right? All right, RSTEM. So, how does MCMC work? As we had briefly mentioned before, it uses this series of discrete iterations. Right? Within each iteration, each parameter has a chance to change its value. So for each parameter, within Stan at least, a new parameter, is sampled at random from the current belief of the posterior distribution, of what we believe the posterior distribution to be at that point. Now, this process differs by the type of algorithm, but we don't need to worry about that. Just know in Stan, which uses Hamiltonian Monte Carlo by default, for each iteration, a proposed parameter gets generated. The posterior values, likelihood values, are then calculated. It's not just the density, it actually includes how the generation process happened as well, too. And then based on a ratio of likelihoods and a random number, we either accept the new proposed value or we reject it. If we reject the proposed value, then the parameter at that step in the chain stays the same. And I'm going to show a plot here of this in just a moment, where you can see where the parameters stayed the same in the chain, because when you look at the time series for it, it's flat. It means that we proposed things, they just were never accepted as they went through. So if the models are specified correctly, so I'm sort of hinting at a bunch of assumptions. If a bunch of statistical assumptions or regularity conditions are met, then, regardless of where you start your chain, if you run the Markov chain long enough, your chain will converge to the posterior. That's magic. I don't really fully understand. I mean, there's proofs to it and all this other stuff. The nice thing about it is that's cool, which means we can take a really complex model, have an initial guess that has nothing to do with it really well, but if specified it properly, let it run, and it gives us the result we want. That's pretty cool, I think. So here's an example of bad convergence. So on the left is beta 0, and on the right is sigma. And this is a chain where I had 100 iterations. I think I had I've got it in here. I did 10 warm-up iterations. and 100 sampling iterations. It basically said the burn-in period is 10, just to show you what would happen if that would work that way. So again, there's 4 chains. They all started around 0 for the mean. And you can start to see what's happening. 2 of the chains for beta 0 start to move toward beta 0's mean. We know the mean for beta 0 should be about 171 if we were using maximum likelihood. So it starts at 0 and it gets up into the 1, right about where it needs to be, right? But along the way, you can see flat parts across iterations. Like right here after like iteration 25, it's flat for several iterations. Those are iterations in which we've proposed new values and it rejected them, right? And so if you don't run the warm-up long enough, you end up getting this chance of having really inefficient chain. Now, if we ran this long enough, we would actually see, here, let's keep the iterations of warm-up the same, run 10,000 sampling iterations. It'll take a little bit longer to run this one. And then, here's what it looks like from a trace plot. Like eventually the chains get there, right? That's the magic of the MCMC I was telling you about. It just takes a really long time for that to happen. And this is the purpose of the burn-in and the purpose of the tune-up, or the warm-up as it's called. And the same thing down here with sigma, although you start to eventually see where it goes. If you were to look at this plot, you could pretty quickly see we need to chop off everything before 5,000 or so. Because up to that point, not all the chains were in the same spot. And if we were to...
I have a question.
Yeah.
There is, like, yeah, I see the chains that swoop up from the bottom, and there are some chains that indicate that zeroed in very quickly, right? Because the caterpillar plot is...
That's right.
Okay, cool.
That's right. And if I look at the density of these plots, you'll see it, right? This is not what you want posterior density plots to look like. This is a non-converged chain, right? So that's a problem in the analysis. In the early days of this, when I mentioned my dissertation with this ETS, I think it was like 2003. We all took a trip out to Princeton, see the campus, the home campus of ETS. They really wanted to see some data. They were using this in one of their testing programs, or trying to. And they had some really strong questions about it. And they showed us all their code, and it was all stuff like this. They hadn't run their chains long enough. It's like, oh, they're not converged. So then we went and promptly gave them lectures about MCMC, and I think it worked better. But anyway, long story short, you see that a lot. When you're not used to a new method, some of the foundational parts are key there. That's why I'm trying to dwell on this a little bit. We had, it was very early, and I don't blame them at all. It happens. So anyway, other questions on this?
Wait, can you go back to the density functions? I think that's what you call them.
The plot right here? Yes.
Yes, so are these of the caterpillar plot that you just ran?
That's exactly right. Yeah, so what I did was I took, this is the what we would call the time series itself. The iterations are on the bottom, the caterpillar plots, if you want to call them that. And then when we don't want, we want to just take a look at the shape of the density itself. We just take all that data, ignore where they were sampled, and pile them into a histogram that's smoothed out. Okay. Yep.
One follow-up question. When we essentially cut off our caterpillar plot, some of that wonkiness would go away then?
Yes.
Okay, great.
Exactly. And that's part of the key.
It's almost like I'm taking a class on Bayesian statistics.
It is. It's almost like I'm teaching a class on it. But you can see what we just did was one of the main types of methods of checking parameter convergence, which is visual inspection, right? And for learning how to do MCMC, I can't encourage you to look at your parameters and your posteriors enough, because they will tell a story that numbers don't really tell. I'm telling you to be qualitative scientists with Markov chains. Now, pretty soon we're going to have a whole well, Lisa has some choice words. I choose not to use them in this class. A whole big ton of parameters that go into the model, right? So you won't be able to plot every one of them, or if you did, you'd be there a long time looking at a lot of plots. So there are ways of quantifying chain convergence. And that gets us into that, right? To look at the posterior distribution, to see if your Markov chain is converged, the label that gets applied to that is something called convergence diagnostics, which is the set of tools you use, or convergence diagnosis for a specific analysis. As you might imagine, since Markov chains have been widespread since the 1990s, there are quite a few methods that have been developed to look at Markov chain convergence. Visual inspection is something I encourage you to do for your small models as you're getting started. But pretty soon, you'll see that the most frequently used statistic is something called the Gelman-Rubin potential scale reduction factor. What? PSRF, which lovingly goes by the term R hat. Why R hat? I have no idea. But that's it. There's a quick reference if you want to see more about it, right here. Never mind. I have to go check that. I actually noted the SAS manual, like in half a page, SAS gave all the math behind it. But think of it this way. What we're actually going to do with these chains is pardon me? Oh, it does work? Okay, so it didn't work for me. What we're looking to do is look to form a ratio of between chain variance to within chain variance. Doesn't that sound like something to you? What's between variance versus within variance? Analysis of variance. It's effectively analysis of variance on our chains. It's not exactly, but it's pretty close. So what we want to say is when between chain variance and within chain variance is approximately equal, we have a convergent Markov chain. So what do I mean by that? So I would say for these chains down at the bottom, within chain variance is roughly equal. There's hardly any of it, right? But if we look at across all four of these chains, between chain variance is quite big. And not only that, within chain variance of the top two chains is actually quite large as well. So this would be an example where if we were to have a measure of between versus within, we'd see a big number that showed up there. And that's exactly what would happen. The R hat would do that. And if we went to Stan's output, it'll actually warn us about that. That's not the warning I wanted. That's not the warning I wanted. Well, maybe I won't get the warning I wanted. But anyway, it will tell you effectively the R hat for each of these. In fact, it'll actually output it. This is the good analysis. This is the good result. But there's a column here that says R hat. We want these values to be very close to 1. The closer they are to 1, the better. And what we'll typically do for a lot of our analyses, and I know I'm out of time, is that we'll look at the biggest value of the R hat as an index of whether the chain has converged. So it becomes a lot easier than looking at every plot. But with that, I need to abruptly end because I hate keeping you late. So we'll continue this, and I'll have that example starting next week. Okay? Homework, no homework, take a weekend off, take a deep breath. Hope to see you next week. And for those of you online, good to see you as well. Have a good weekend.
Hey, Jonathan, can I ask you a question?
One moment.